as opposed to my applied force? Constant. We know that gravity is going to pull you to the center of the earth at 9.8 at 1 g, right? That's the acceleration due to gravity. Whereas when we did the method of me applying the force, right? So I'm gonna just rewrite what we just did in the beginning here. So this is a flat surface when there was no inclined plane. Call it level surface. So at level surface, we had Fg and Fn, and net force equals 0. So we calculated frictional force mu F of n, right? And we had mu is equal to frictional force over F of n. And we got, what was our example? What was the mass? Matusala, what's our mass?
It was
6.25 kilograms. Or was that newtons already? I think that was the Fg already, yeah. So that was already in newtons, so that's the Fg equals mg. So the applied force is frictional force, and that was, did we use 1.5? Okay, so we're gonna use those numbers. So we did 1.5 divided by 6.25, and you got 0.24. Okay, so let's keep that in mind now. Now we're gonna look at inclined planes and frictional force. Okay, so here it is. And we did some activity where you got to measure the angle. Okay, now that you know how to measure the angle doing that, we are gonna use 18. I'm gonna just not deal with the 0.5. I'll just go 18 for the sake of easy calculation here. Okay, we're gonna go 18 degrees. We should actually use 18.5. You know that it's not gonna be exactly 0.24, okay? Because I'm rounding off, or I actually rounded down. So here's the block. Here's what we did. We let the block just sit on the surface. I lifted this table until it just began to move. So let's write down the FBD. So go ahead and do the FBD. So you've got Fn. And where would the friction be? So let's say you went this way, and I'm gonna put net force here, which is equal to 0, but I'm gonna write that there. So your frictional force is the opposite of the motion going this way, right? Now be careful here. Before you actually copy this part, I want you to just watch, okay? So what is that force right there?
Fg.
That's Fg. So I'm gonna write down Fg this way. Okay, now take a look. Your Fn is no longer equal to your Fg, right? Because look, this is Fn, and your Fg, as you can see, they are not in opposite direction. Is not exactly in the opposite direction. There's some angles between them. They're not equal. They're not going to balance each other. So what will balance F of n? Yeah, right here. This is your Fg of y in the vertical direction, right? So Fn is actually equal to Fg of y. Now you see here, this part, this can be the tricky part. That little bit right there should be parallel with the actual inclined plane. They should be like the number 11, two straight lines parallel. So that you have to make sure that it's 90 degrees between the x and the y, and this is your Fg of x. Okay, let's talk about what Fg of x and Fg of y are actually doing here. You know that Fg is equal to mg. We know that. But what is Fg of y? Well, let's take a look at what is that angle 18 degrees congruent to in that triangle within a triangle. This is 90 degrees, right? You see that angle is actually congruent to this angle here, mathematically, and that would be 18 degrees there. So you'll just have to, again, we did somewhat of a geometry proof the other day with two lines that are 90 degrees transected like that, okay? So they will be congruent angles. So if I were to solve for Fg of y, which is right here, and I know my Fg is just mg, that's easy, right? So I'm going to use the FG as a frame of reference. It's a constant force because of the G being constant. So the FG of Y will be what? You have an adjacent and hypotenuse. Adjacent and hypotenuse. So this would actually be your FG cos of theta, which is 18 degrees, is the theta. What about, okay, well, what is FG of Y actually doing then? What is it doing in terms of this? Is FG of Y actually making the box or the block slide down the inclined plane? No, it's not. Well, what is it? This is also known as the perpendicular force. And it has nothing to do with the falling or the sliding of the block, but it is actually equal to the normal force. This is equal to the force of the table pulling or pushing up on that block. Okay? So that's what FGY is doing. It's just a surface force equivalent. What about the FG of X? What is this dark line, arrow going down, actually doing to that block? You see, this is the inclined plane. And this is that force. They are parallel. So that means the FG of X is actually the sliding force. You can call it the force that is actually causing the block to slide down the incline. See, that is exactly parallel with the inclined plane. That is what's doing the sliding here. Okay, so when I pulled that table higher and higher until that angle is the correct angle to just break that static coefficient, that is the sliding force. Okay, so this will be FG of X is equal to FG, look that, opposite over hypotenuse, sine theta. Okay, so we have those two forces now. We've got FG cos theta for the Y and the FG sine theta for the X. Okay, so just like with anything, so you have your FBD, start with the FBD, done. Now what do we do next? X and the Y component, because they're different, right? So I'm going to start with the X component right here. What are the forces in the X component? So we always go with net force on the X is equal to, this is positive, what else goes with it? Look at all the forces that is going down with the direction of the net force, down as in down the inclined plane. Fg of X is also going with it. What's opposing it? Frictional force. So how do you write the net force on the X? So Fgx minus frictional force equals 0. Why do we say it's 0? Because it just started to slide. You're looking at that angle when it just started to slide. You didn't yank the table up so that it's sliding already and it started to accelerate. It wasn't accelerating because I yanked it and it just started to slide. And by the way, even when it was starting to slide, you notice that the sliding is actually constant. It's not accelerating. Once I broke the inertia at rest and the block started to move, it started to move at whatever velocity that is. So it's still net force of 0. Okay? What about the Y components? What forces are acting here? This is going down because gravity always goes towards the center of the earth. That's Fg. So the Fg of Y must also go down. Fg of X must go down with the inclined plane. That's how things go, right? Okay, so if this is Fg of Y and the Fn is exact opposite, what can you say about the net force on the Y? 0. Why is that? How do you know? It's not going up and down. It's not jumping up off the table. It's not sinking into the table. So the net force on the Y is equal to Fn minus Fg of Y equals 0. Is that okay? That's how you know it's equal to 0. It's stable. This is a static equilibrium at first, but when it started to move, you have dynamic equilibrium. It's still in a state of equilibrium. Okay, so
Would it still be dynamic equilibrium in the Y though? Because like even when it's moving,
yeah,
along the
it's
Y-axis,
covering.
it's not really.
Yeah, it's covering the, it's going down in terms of the inclined plane, but we have defined the y-axis not in the vertical direction anymore, not like FG, but it's like because of the inclined plane becomes your frame of reference, that is your X now. So if you think of how we used to look at it before, it was just like that. And it would be easier if we can ignore everything else for now. I'll show you. It was just like this, you see that? And this is the X, and that is the Y, like that. And now this is no longer the Y. So if you're looking at an inclined plane, you're gonna have to tilt your head a little bit, and whatever table or surface is the inclined plane, that becomes your X.
Yeah. But
Yeah.
Would it be it? But would you consider the net force on the Y to be a dynamic equilibrium? Because technically it would be,
No,
be static all the time.
it didn't move because the box just followed FG of X. Yeah. Make sense now?
Yeah.
Because I know you're thinking it lowered in altitude. It went lower, right? Because it went down, so did it not go down in the y-axis as well? Well, you could think of it that it went down, but really it is just actually going with the X. It's just going with the X. It just happened that the X is now inclined. Okay? All right. So, what are we solving for? We are solving for the mu. That's what we're looking for. This is the ultimate question. All these things lead to the question of what is mu. So how do we solve for that? Yeah, okay. So I'm going to just write down the frictional force, mu F of n, right? So then you go, well, to find the mu easy, I just go frictional force over F of n. That's the equation. Now, we got to find what frictional force is first, which is here. And we got to find the normal force is, which is there. We need to somehow combine them, and unite them somehow. So, we're going to start breaking it down before it gets connected. FGX equals FF. There you go. There's your FF. But how do we get the FG of X? What's FG of X? FG sine theta equals frictional force. Now, do we know, we have the angle. Do we know the FG? We're using one single block this time, right? So we're not going to use a 6.25 Newton. What is the weight of one block? Do you guys remember when I lifted it? 2? Okay, so this would be 2, was it just 2? Okay, yeah, I think so, right? 2 Newtons. So 2 is the FG times sine of 18, and that gives you your F of F. All right, so let's come up with that number. Okay, you guys calculate this for me. Let's see what you have. I'm on degree mode. Times 2. What you get? 0.618 Newton. Did you get that one? Okay. All right, so we have the frictional force, 1 down. Okay, now we got to find the F of n. Where is F of n? Right here. So F of n is equal to FG of y. Okay, so what's FG of y again? FG of y, adjacent and hypotenuse. So FG cos theta. So 2 is the weight times cos of 18. And what's that? What is it? 1.9 newtons. Okay, so we have those two numbers. All right, so let's see what we have for mu. Mu is then frictional force over F of n, which is 0.618 divided by 1.9, and we have 0.33 with this one. This method gave us 0.33, and the one where I pulled gave us 0.25. What would you trust? The second method with the inclined plane or the first method where I pulled it? What do you think would give you the more constant force? What do you think? And trying to eliminate the error of measuring the angles. Now the errors would be measuring the angles for the second method, right? You have to measure the angle with the protractor, and then the other method that you did was you're measuring the legs of the table and subtracting it and doing your geometry, trigonometry, right? So eliminating all the errors from that, what would be the more accurate method? The inclined plane or the person pulling? What do you think?
The incline, because you have you're using 2FG. So the X and Y, you're using two constant.
Yeah, you're using, well, first of all, the gravity will be more constant because of the G, right? No one is pulling it, so the applied force could be inaccurate. But also remember that this thing here, I'm not sure if I use the same block. I may have put it down and I wasn't sure if I was using the same block because I put them down and I picked up a block. So that could be different also, and I also where I put the block may have affected that as well. But 0.3 and 0.24, that's not far off. So we could say that your desk has probably a mu between 0.24 and 0.33, which, by the way, if you look at a chart of mu, which there will be, like ice on ice, rubber on concrete, they have, if they're doing a forensic files investigation, they can calculate it at that time depending on the atmosphere or the weather and the conditions of the road. They can do these calculations quick enough with the same thing that you did. So they grab something, let's say it's made of rubber, the tire, they'll just pull it, okay, and they'll calculate the mu with the method that we did right here, and they'll get an idea of the mu. Okay, we'll do one question like that where it actually solves a lot of traffic problems in terms of calculating if the person was speeding or something like that. And you can't lie when physics is used that way. Okay, so that is the application of inclined planes with friction. Okay, so I'm gonna go back to the beginning of lesson 3 here. So the components of the force of gravity. All right. So the goal one is to solve problems involving frictionless surface at an incline and involving surfaces with friction at an incline. So we actually went and did the friction first. So we're gonna look at frictionless. Okay. So up to this point, we've always seen normal force acting in the upward direction like this. So that is the cases where there's no inclined plane. And then, of course, I'm going to just rewrite what we just did earlier. So this is your FG, and this is your FG of Y, and this is the FG of X. Okay, same thing here. Okay, so the point is your Fn is no longer equal to Fg when you're dealing with inclines, and your Fn is actually equal to the Fg of Y. Okay, so that is the case with inclined planes. So you're not really getting, like for example, if I free fall, if I drop this pen, just dropped it, what made it fall? What force made it fall? The Fg, right? So the Fg, once it touched the table, Fg becomes Fn. Okay? When you have an incline, you're not getting the full force of gravity because the surface is taking away from that. That's why they're not equal. Okay, let's take a look at this example. This one will be easier for you now because we actually dealt with something real and something harder there. So example 1, the two diagrams below depict the free body diagram for a 1,000 kilogram roller coaster. So that gives you the mass right there. On the first drop of 2 different roller coaster rides. Okay, so you have different inclines here. determine the net force and acceleration of the roller coaster car. So you have two different situations here. So I'm going to call this one situation A and situation B so we can distinguish. Okay. We're looking for two things, right? Net force and acceleration. Okay. All right, so you have this picture. What is the first thing? How do you deal with a question like this? What's the first thing that you do? This is what you're looking for. I'm just going to write down, those are the question, but how do I get there? Can you tell me what is net force equal to? Newton's second law tells you what? MA, always. Net force is MA. That's the formula for net force. But when we do an FBD equation for net force, not just MA, it actually has to do with what is happening. So you see you have that, and you also have this, right? So we need to label what those are. Where is the FG? Right here. So that means this is your FG of X, and this is your FG of Y. Okay, so you're looking for net force, and the object is just going down along the X, as in the surface. What's the formula on the X? Yeah. And can I put 0 in this case? Is there, wait, first of all, is there friction? Hang on. Oh, it says negligible effect. Okay, so this actually we can ignore. It actually did say negligible. So what is the net force on the X then? Isn't that just FG of X? Yeah, there's no friction. We can ignore it. It says negligible. So how do we find the net force? So MA is equal to mg. What's the X? There's the X right here. Opposite and hypotenuse. Opposite right here. There's the angle. There's the angle 45 degrees. So this will be sine theta. Okay. You have to follow the rules of trigonometry. You can't just always think that X is cos. Okay? Because your frame of reference here has changed. Yeah. So X is sine because that's the angle. It depends on what angle you're using. Okay? Because the angle is taken from the vertical this time. Okay? So we're looking for the net force. So net force is M. Do we know the mass? Do we know the mass? Do we care about the mass? Look at where we're right now. This is where we're at. So then you go, mass is unknown, right? I'm going to just say mass is unknown at this point. It is not given. So then we get to the point where, well, net force is equal to mg sine theta. You go, I can't solve this because there's no m. Well, but you have to expand it because you just told me that net force is ma, so I wrote it down.
Could you cancel the ends on either side?
So just because I ask you to find the net force and acceleration does not mean you need to do that in that order. So here I actually need to find the acceleration first. So now you've got 9.8 sine of 45, and that's going to give you the acceleration. And then you can go back and find the net force. Okay, somebody want to give me that number? 6.93? Yeah, 6.93 meters per second squared. I don't have any given. It actually says 1,000 kilogram. I'm going to ignore the fact that I have 1 sig fig in 1,000. I'm just going to leave it at 6.93. Now that's the acceleration. We can find the net force now. All right, so, but first, we don't have the mass. Again, we're back to we don't have the mass. We have the acceleration. How do we find the net force? How do we find the net force in this case? Oh, wait a second, mass is actually given. This is only if m is unknown, you can cancel the mass. Yeah.
Oh, I thought you were doing that just to prove a point.
Yeah, I was just making a point there actually. And you picked it up, Nick, so fast. Yeah, if mass is unknown, you can cancel it, right? But you can't find the net force if mass is unknown. But we do know the mass, right? So it's 1,000 times 6.93. So that would be 6,093. 6,930 newtons is the net force. That makes sense?
I didn't look at it, so I
Mm-hmm.
mean, sense.
Yeah, because you found the mass, you know that mass is given, then you just plugged it in and you got your net force first. Yeah. What about B? Now you got a different one. That's gonna go faster. Hang on a second. We can actually extend this as well. If we know the time that it took to go, we can figure out the speed of them going down, right? Because the acceleration is given. We know the acceleration. We'll assume that the velocity at the top, V1 is 0, okay? And we know the time. If we know the time, we can figure out the speed at the bottom. Okay, but we won't get there. Okay, so same thing here. You're looking for two things, net force and acceleration. Okay, so would that be something that you want to try now, or should we go on to example 2? You want to wait for it and do it on your own? Yeah? Or you want to try it now? Why don't you try it now? Yeah, let's try it now quick. It shouldn't take you long to do. And we can move on from here.